Hello mathematicians, thank you for joining me today as we're going to look at calculus proofs today. So we've been spending a lot of time doing different types of proofs, and today we're going to try to use it in some way that you would see in calculus. And so if you continue on and you take analysis or advanced calculus, you'll see a lot of proofs like these. In order to go through these proofs, what we're going to need is the triangle inequality, and that is if I take the absolute value of x plus y, that is less than or equal to the absolute value of x plus the absolute value of y. So to see this, I'm going to just pictorially look at what this means and why it's called the triangle inequality. The reason why this is called the triangle inequality is the idea is that if I take a value x in the two dimensions, here's x, here's y, if I add it to it, what I end up with is here's x and here's y. But if I take x plus y, I just get this side. And so the idea is I end up with a triangle with points A, B, C. And the idea is if I move from A to B to C, that's going to take longer than going directly from A to C, which would be my x plus y. Therefore, x plus y is always going to be less than or equal to x plus y. Now, if we're dealing with real numbers instead of dealing with things in r squared, what we get is a picture that looks like here's a number line. So here's x. If I add y, this would be x plus y if x was positive and y was positive. So x plus y would actually be equal to x plus the absolute value of y. Whereas if y and x went in different directions, what that would mean is I'd move this far in the x direction, then this far in the y direction. And so x plus y in this case would just be this portion here. But if I move the absolute value of x and the absolute value of y, I had to move farther to get here than if I had just gone directly from here to here. So what we have here is the formal definition of a limit. That is, we say that the limit as x goes to c of f of x is equal to L if, for all epsilon greater than 0, there exists a delta greater than 0, such that the absolute value of f of x minus L is less than or equal to epsilon for all x in R that satisfy 0 is less than the absolute value of x minus c is less than delta. So just to point out, there's a lot going on there. Trying to parse through that with our symbolic logic, it's just there's a lot happening, and that's what makes some of these epsilon delta proofs difficult, and there are types of things that people talk about a lot because they remember, oh my gosh, I had to do all these things. Well, they're not too bad, and they are fun, but you need to be really careful about the definitions along the way. So notice that if we're looking at this, this is a for all proof. So you have to show for every epsilon. It's also an existence proof. So we have to show the existence of a delta for any arbitrary epsilon that satisfies, well, if I can, for all epsilon, I can find this delta such that, well, I can make the difference between f of x and L less than epsilon as long as I stay within delta of x. So that is, as long as my x's are close to c, my function value will stay close to L, and so I have to be very careful and very precise to show every one of these steps when I'm doing an epsilon delta proof. So we'll just start off with, let's show that the limit as x goes to 5 of 8x minus 3 is equal to 37. So we'll go through and we'll have to talk about epsilons and deltas, and we'll make our way through the whole proof showing that this is indeed true. All right, so now we want to show that the limit as x goes to 5 of 8x minus 3 is equal to 37. Well, remember how we did that was we have to show that for all epsilon greater than 0, there exists a delta greater than 0 such that f of x minus L is less than epsilon whenever 0 is less than x minus c is less than delta. So the idea of the proof is that we're just going to let epsilon greater than 0 be given. So we're going to let this be arbitrary so that this will work for all epsilon. So that's given to us. What we then have to do is we have to find a delta. So we're going to choose a delta greater than 0. And I'm going to leave that blank for now because I'm going to fill in what delta is going to be later based on what I need. My then is going to be then f of x minus L is less than epsilon when 0 is less than x minus c is less than delta. Now, in this case, what I would do is say, well, what is f of x? What is L? What is c? And so what I would have to show is then, well, f of x is 8x minus 3. I have to show that that minus L is 37 is less than epsilon when 0 is less than x minus 5 is less than delta. So that's what I need to get out is based on some delta. I have to find, well, let epsilon be greater than 0. I have to find a delta so that this is true. Well, now, if we think about how would I show this is true, is I'm going to start on the left, and I'm going to do things until I get to the right. So I'm just going to start with 8x minus 3 minus 37, and hopefully I can simplify this to somehow get out that this is less than epsilon. Well, what I have is this is 8x minus 40. So I can factor out an 8, and I get 8 times x minus 5. Well, now the absolute value of a times the absolute value of b is the absolute value of a times the absolute value of b. So I get the absolute value of 8 times the absolute value of x minus 5. But the absolute value of 8 is 8. So I get 8 times the absolute value of x minus 5. Now the whole point here is that I get to assume that the absolute value of x minus 5 is less than delta. So I'm going to need some more room. I'm going to write this out, but I get that this is less than 8 times delta because the absolute value of x minus 5 is less than delta. Now what does that mean is, well, the goal is to show that this is less than epsilon. Well, since I get to pick delta, I just want to pick a delta so that 8 delta is equal to epsilon. So let's pick delta is epsilon over 8. And what I get is 8 times epsilon over 8 is just epsilon. And so indeed, if x minus 5 is less than delta, then we get that 8x minus 3 minus 37 is less than epsilon. So we have now proven that the limit as x goes to 5 of 8x minus 3 is indeed 37. Now for another example, let's look at the limit as x goes to 2 of x squared minus 1 and show that that is indeed equal to 3. All right, now we're going to work on another limit. So we're going to say let epsilon greater than 0 be given. We're going to end up choosing a delta so that f of x minus L is less than epsilon as long as 0 is less than x minus c is less than delta. Well, if we look at it in this case, what we had was f of x is x squared minus 1. My limit is 3, so I'm going to subtract 3. And I want to show that's less than epsilon whenever x minus 2 is less than delta. So what I have is, well, this becomes x squared minus 4, which is then x plus 2 times x minus 2. So in absolute value, this is the absolute value of x plus 2 times the absolute value of x minus 2. And what we know is that we can assume that x minus 2 is less than delta, so we get this is less than the absolute value of x plus 2 times delta. Now the goal is to show that this is less than epsilon. So last time what we picked was, well, it was 8 delta, so we said let delta be epsilon over 8. Well, notice I can't let delta be the absolute value of x, or epsilon over the absolute value of x plus 2 because x's variable is changing. I have to pick a specific number. I can't just say, well, let it be based on x. So what I have to do is I have to think about this in some other way to say, well, can I pick a number so that I know that absolute value of x plus 2 has to be less than that number? Well, in general, maybe not, but notice I get to pick delta. So if I let delta equal 1, notice that, well, the absolute value of x plus 2 is equal to the absolute value of x minus 2 plus 2 plus 2. Why is that helpful? Well, because this is just x minus 2 plus 4, so if I use a triangle inequality, I get this is less than or equal to this number plus the absolute value of this number. So this is less than or equal to the absolute value of x minus 2 plus 4. Now, the reason why we did that is we wanted this x minus 2. So the point is we get to assume that this is less than delta plus 4. Now, if I was going to use delta plus 4 over there, that's fine, but then I'm going to have to figure out what epsilon's going to be, and that's going to become difficult. So if I just say, oh, well, let's let delta equal 1, then this is equal to 1 plus 4 is 5. So if I know that delta is 1, then this is equal to 5 delta. However, if delta is 1, that might not be good enough for the epsilon. So what I'm going to need is I'm going to want 5 delta to be equal to epsilon. So what I should do is I also want delta to be epsilon over 5, so I can put this is 5 epsilon over 5 is equal to epsilon. Well, now I can't pick two deltas. I can't pick it to be 1 and epsilon over 5. But at each point I just want less than. So instead of doing that, what I'm going to do is I'm going to pick delta to be the minimum of 1 and epsilon over 5. Now, if I pick that, what I get is because delta is less than or equal to the minimum, I have that this is less than or equal to 1 plus 4, so this is less than or equal to 5 delta. But delta is also less than or equal to epsilon over 5 because it's the minimum of 1 and epsilon over 5. So this is less than or equal to 5 epsilon over 5. So what we get is, combining these together, f of x minus L is less than epsilon as long as 0 is less than x minus c is less than delta. We can also have that the limit does not exist. So what would it mean for the limit to not exist would be, well, we'd have to show that the negation of the limit existing is true. So if we go back to our formal definition of limit, we have to show that the negation of that statement is true. All right, we now want to show that the limit as x goes to 0 of 1 over x does not exist. So how do we show a limit does not exist? Well, we have to show the negation of the limit does exist. So we'd have to do something along the lines of, well, if we negate it for all, we get a there exists. So there exists an epsilon such that for all delta, we have that there exists an x where 0 is less than x minus c is less than delta such that f of x minus L is greater than or equal to epsilon. So I would have to prove that. Well, now proving that really comes down to negating it so that we can do a proof by contradiction. So when we're proving this, what we're actually going to do is a proof by contradiction by assuming the limit exists. So by way of contradiction, assume that the limit as x goes to 0 of 1 over x exists, so it's equal to L for some real number L. Then what I get is that for any epsilon, there exists a delta such that 1 over x minus L is less than that epsilon. So let's just pick an epsilon as then, let's say epsilon equals 1. If epsilon equals 1, there exists a delta such that absolute value of 1 over x minus L is less than 1 for all x satisfying 0 is less than the absolute value of x minus c is 0, so just the absolute value of x is less than delta. So now what I want to do is focus on this portion and say, okay, the absolute value of 1 over x minus L is less than 1. So what that means is that negative 1 is less than 1 over x minus L is less than 1. So to solve this inequality, we end up with negative 1 is less than this is less than this. Well, what I want to think about here is that if I add L to both sides, I get negative 1 plus L is less than 1 over x is less than 1 plus L. So in order for this to be true, that means that 1 over x is between negative 1 plus L and 1 plus L for all delta, or for all x less than delta. So that means that we always have to have this be the case because we said the limit exists and was equal to L. However, if we actually look at 1 over x as we approach 0, what's going to happen is this is going to get arbitrarily large in either the positive or negative direction, depending on whether x is positive or negative. So we know that eventually, on the positive direction, it's going to be bigger than 1 plus L. On the negative direction, it's going to be smaller than negative 1 plus L. So what we have to do is we have to prove that that actually happens. All right, so what we want to point out here is that if we take 1 plus L, this is going to be a real number. I don't know what else it is, but it's going to be a real number. So because it's a real number, we can always find a natural number, n, such that 1 plus L is less than n. So there exists an n in the set of natural numbers such that 1 plus L is less than n. If this is negative, 1 would suffice. If this is 10 billion 0.750, I round up to the next number, and there's my natural number. If this is a natural number, I add 1, and I found a bigger natural number. So I can always find a natural number bigger than any real number. Now also, if I take delta, notice that delta is non-zero, and is actually positive, so 1 over delta is a positive number. Therefore, it's a real number, so there exists an m in the set of natural numbers such that 1 over delta is less than m. Right, then what I'm going to do is I want to define x, and I'm going to let x be 1 over the minimum of m and n, or the maximum actually of m and n. So I'm going to take 1 over the maximum of m and n. Now what I want to point out about x is that x is, well, since the maximum is bigger than or equal to m and m, this is going to be less than or equal to 1 over m, which, since m is bigger than 1 over delta, 1 over m is smaller than 1 over delta, so this is less than delta. So if I pick x to be 1 over the maximum of m and n, I get x is less than or equal to 1 over m, so therefore it's less than delta. Now, again, I'm picking here, since I'm taking 1 over the maximum of these are both positive, x is going to end up being a positive number, so therefore the absolute value of x is going to be less than delta, because they're both positive and x is less than delta. Now, if we focus on the n part, what we get is that 1 over x is equal to 1 over the max of n and m. So now if I simplify that, 1 over x is just the maximum of n and m, which is greater than or equal to n, but n is greater than 1 plus L. So what have we just shown? We found an x where x was smaller than delta in absolute value, but 1 over x was bigger than 1 plus L. Therefore, we got a contradiction to the fact that 1 over x minus L is less than 1 for all x within delta of 0. So we have found a contradiction. What does that mean? Well, that means that the limit as x goes to 0 of 1 over x does not exist. Now, if we remember calculus, what we recall is that we used limits in order to define derivatives. And derivatives were a major topic that we talked about in calculus. So if we remember the definition, it was that if we have a function, then the derivative at the point A is given by f prime of A is the limit as h goes to 0 of f of A plus h minus f of A all over h. And so if this limit didn't exist, then we say the derivative at the point doesn't exist. And so if we wanted to find a derivative function, we'd find the derivative at all points. And so what we'll do is we'll go through an example of using the formal epsilon delta definition of a limit to find the derivative of a given function. So our derivative example is going to be let f of x equal x squared. We want to show that the derivative at a for any real number a is just 2a. Now we're going to work with the derivative, and we want to show that if f of x equals x squared, the derivative at the point A is just 2a. So what does that mean? Well, remember the derivative is defined as the limit as h goes to 0 of f of a plus h minus f of a all over h. And so what I want to do is I want to show that this is equal to 2a when f of x is equal to x squared. So I want to show that if I plug this in, the limit as h goes to 0 of a plus h squared minus a squared all over h is equal to 2a. So if I want to prove that the derivative at a is just equal to 2a, I have to prove that this limit is equal to this. All right, to set this up like another limit, we would just say, okay, let epsilon be greater than 0 be given, and I have to find my delta. So what am I going to do is I'm going to take my function. My function here was a plus h squared minus a squared all over h. And I want to subtract my limit, which was 2a. Now, eventually, I want to show that's less than epsilon, so I'm going to try to simplify it. Well, to simplify it, I notice I have two fractions, so let's turn it into one. So I'm going to get a plus h squared minus a squared minus 2ah all over h. Well, next I can say, well, this is just a squared plus 2ah plus h squared minus a squared minus 2ah all over h. And so now I'm starting to see things are going to cancel out. So I get a squared minus a squared. I get 2ah minus 2ah. And so what I'm left with is h squared over h. So I've started off with f of x minus L. I simplified, and now I'm down to h squared over h. All right, since I need more room, I'm going to go back to the top and start with that. And notice that I have the absolute value of h squared over h. Now, recall that we said that 0 is less than, in this case, h minus 0 is just the absolute value of h is less than delta. So I get to assume that. What that means is that h is not equal to 0. Because h is not equal to 0, h squared over h is just h. So that's important that we're not letting it be 0, because then 0 over 0 is undefined. But as long as it's not 0, that's just h. Well, I know that the absolute value of h is less than delta because that's what I get to assume. So now all I have to do is find a delta so that this is less than epsilon. So I just let delta equal epsilon. Therefore, that's equal to epsilon. So what I found was that f of x minus L is equal to h squared over h is just the absolute value of h is less than delta by assumption. So we can choose our delta to be epsilon. So we get, indeed, that our limit was equal to 2a. Hence, the derivative of x squared at the point A is always going to be 2a. Today we looked at some different calculus proofs. We looked at limits using the formal definition to prove that a limit exists and is equal to something, or proving that a limit does not exist. We also talked about derivatives, and we showed that the derivative of x squared was, well, at a was 2a for any real number a, using both the limit definition of derivative and the formal definition of limit. And so these are the types of proofs you'd again expect if you move on and take an analysis or an advanced calculus class. So I wanted to give you a heads up on some of those, but also go back to over some of the calculus stuff from your calculus class so you can see how those things would work if you're formally proving them.